What's up, guys? This is Mr. Carlson, C Squared Mathematics. Welcome back. We're now going to skip past 6.4 because we're not going to actually learn that. We're going to go right to 6.5, trigonometric equations. And so this is a two-part lesson. So we're going to do part 1 or 6.5a today, and then 6.5b, which is a lot shorter. That's going to be tomorrow. We're going to go through bell work, homework quiz, and then through the lesson. This is the only question I have for bell work that I want to kind of get through. So it's very reminiscent of what we did in the previous video for 6.3, and I hope that we kind of learned a lot there and the structure of half angles and double angles. So right here, first thing I want to notice is this. This is my actual interval, okay? They tell us secant of alpha equals negative 17 all over 15. Okay, so I'm given this. I need to know exactly which quadrant I'm actually in. So this is pi over 2 to pi, which means I'm in the second quadrant, okay? So I'm going to go over here. I'm going to actually draw my second quadrant. That's like the first step that I need to do. I'm going to draw my second quadrant. This is my alpha. Now, this is alpha, not alpha divided by 2. It's not my half angle. It's just my regular angle, okay? Secant, negative 17 all over 15. Well, secant is the reciprocal of cosine. So that means if cosine's adjacent all over hypotenuse, that means secant is hypotenuse all over adjacent. So 17 is my hypotenuse. And then adjacent is 15, and make sure I get the negative on there. Now, when I do Pythagorean theorem, I do get this to be 8. So I need to make sure I put that in there as 8. Also, make sure that you know how to use the Pythagorean theorem, but I'm not going to show you how to do that. You should already know. If you don't know the Pythagorean theorem, then yowzers, like yikes. Make sure you know how to do that. That's 8. Now, let's go through our actual A, sine, B, cosine, C, tangent. So, first thing I'm going to do is sine over here. So, sine of my half angle. I don't really care what the angle is. I'm just evaluating it. I want to find the exact value. That's what I'm trying to do. So my formula is going to be plus or minus. Now we don't really want to put plus or minus in there because my formula does say plus or minus, and let's just give you the whole formula right here. It's plus or minus, and then this is 1, and then minus cosine of alpha all over 2. So this is my formula, right? I probably won't give you the other formulas because it's kind of tedious. And I don't want to do plus or minus, so I need to figure out which one it is. Is it plus or is it minus? The way you do that is by using your interval. Okay, so pi over 2 is 90 degrees, and then this is 180 degrees. So I need to divide this by 2 in order to get my alpha all over 2. So then this is going to be 45 degrees, alpha all over 2, and then this is going to be 90 degrees. So this is my new interval. Since this is my new interval, I can tell that this is actually in quadrant 1. So since it's in quadrant 1, I'm actually going to use plus for all of them. Okay, I'm going to use plus for cosine, I'm going to use plus for tangent, and sine. So that means I'm not going to be using my negative at all right there. I'm going to erase that. Okay, that is how you know if it's going to be positive or negative. You have to look at your interval and then divide it by 2. And now you can see 45 to 90, that's in the first quadrant, which means everything's going to be positive. Now remember, if you're like, this is the second quadrant. No, well, it is, but this is the second quadrant for my alpha, not my alpha all over 2. There's a distinction. My alpha all over 2 is in the first quadrant. So if I divide this angle by whatever angle that is, okay, if I divide that angle, okay, and then I get into the first quadrant, then you can see how alpha over 2 is in the first. So let's go to town. I don't want to waste any more time. This is going to be 1 minus, what's cosine of alpha? Cosine of alpha is negative 15 all over 17. So this is going to be negative 15 and then all over 17, and then divide by 2. So this equals, this is going to be plus plus, and I'm actually going to do one quick step here. So this is 17 and this is 17, right? So 17 plus 15 is going to be 32. So this is 32 all over 17. And then I'm going to multiply by 1/2 here. Okay, I'm going to kind of do that step all in one. So then now what I have is 32 all over 34. So we simplify this down. We can reduce this. Actually, let's reduce this. This is probably divided by 2. So this is going to be 16 and 17, right? So 32 divided by 2 is 16, and then this divided by 2 is 17. So that means I have 4 because that's the radical, and then right here is 17. And so this equals 4 radical 17 all over 17. So not too bad, okay? I skipped a lot of steps there in between, but I think we've done enough practice to be able to recognize what I'm doing here. So I hope that's the case. Let's do cosine. So B, cosine, alpha all over 2. I still get the positive. Now, I'm not going to go and give you the formula here. All you guys need to know is that it's going to be positive cosine instead of negative. So positive, this is going to be 15 all over 17. I am going to skip around, so try to pay close attention. I already know this is going to be 17 all over 17. This 1 right here is going to be 17 all over 17, so it's going to be 32 all over 17, and then divided by, oh, sorry, this is negative. I was like, it cannot be the exact same thing. That's ridiculous. Okay, it is definitely not the exact same thing. It's going to be 2 divided by 17. Because this is going to be right here, guys. This is going to be 17 and then all over 17 right there. 17 minus 15 is 2. And then, of course, 1/2. Those go poofy, so I'm left with 1 all over 17, but the whole radical. And so now I have 1 all over radical 17 because 1 is a perfect square. So this is radical 17 all over 17. And of course, it's still plus because we're in the first quadrant for my half angle as per my interval. Okay, let's go to C, tangent. Tangent's really easy because I'm just going to take sine all over cosine. So sine is that, so 4 radical 17 all over 17, and then divided by radical 17 all over 17. And so now you can see, I hope you can see, is that this radical 17 all over 17 will go poofy with that whole thing. So I just have 4. That's all I have, okay? So that one was really nice. And of course, since we finished, a lovely unicorn with a freckle. Couple freckles, whatever. We're done, okay? We're done. So that is how you do a brief reminder of how you do 6.3 double angles and half angles. We didn't do a double angle here. We just did a half, but I hope that still makes sense. I'm going to erase, and so you guys can get started on your homework quiz. You have 30 minutes, 5 questions, and then afterwards get started on 6.5 part 1, 6.5a, okay? Remember to review your answers and send any partial credit requests to me. So 6.5a, we're going to do this as part 1. How do I apply identities to solve trigonometric equations? Okay, this is going to be kind of an ongoing essential question because we're really going to deal more with identities in the next day in part 2 in 6.5b. But not really today. However, we are still going to be using a lot of identities kind of implicitly, just not as explicitly, okay? So it's still a good essential question, and that's going to be our essential question for the next 2 days. How can I solve a trigonometric equation by using an inverse trig, multiple angles, quadratic factoring, GCF factoring, all this stuff? Okay, you can solve a trigonometric equation by using all of this fun jazz, okay? And by calculator, of course, what I mean is Desmos. And I'm going to show you how to do that in a little bit, okay? So this lesson, there's a reason why there's a reason why it's split up in 2 parts, guys, because it can be rather long. But I'm going to try to, but it's not hard concepts. Like 6.2 was a rather hard concept, like because all of the math and all the simplifying and the radicals. 6.3 had a lot of radicals you needed to simplify. 6.5 What makes it kind of hard is just that you have to analytically think about the unit circle here. So make sure you have your unit circle out. Okay, and you also have to analytically think about different identities and how you apply them in different ways. Okay. Hopefully, I want to get this actually started here. Hopefully, it will kind of solidify in your brain what specifically like what we're doing and how we're solving trigonometric equations by using a graph. So I'm actually going to pull up this trig functions in the graph. I'm going to pull this one up. This is something that I've already been given to you, that I already gave you. If you go to your Google Classroom, classwork, scroll down, and remember you have your Desmos. Right here. You may have to say view more, but it's Desmos graphs. So this is the unit circle I'm using. This is the general trig functions that I will be also using, and this is just all complete. I'm not going to really be using that one. I'm going to be using this one right here, okay? So I'll show you graphically, trigonometrically, and then algebraically how to solve these equations. But first, let's get into it. So some trigonometric equations are true for all values of x. So what does that mean? That means you have a trigonometric equation like this. Clearly, this is always going to be true. Those equations are what we call identities. Okay, we already did that. Okay, so some trigonometric equations are true no matter what, always, 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 always. Okay, and so this is what we call an identity. We've already done that before. We actually did multiple identities, sum and difference, double and half angle, and then how to verify them. That was 6.1, 2, and 3. Now, some trigonometric equations, though, are only true for certain values of x. So they're what we call conditional. They're conditional equations. So verifying identities were not conditional. It does not matter what this is. If that x is the same thing as that x, it will always equal 1 no matter what. But now what we're going to be doing is what we call conditional equations. So I'm going to ask you which values of x make this equation true. Tangent of x equals 1. Tangent of x equals 1. What value makes that true? Okay. Well, first of all, I'm probably going to think the main value, pi all over 4. Okay, so if I plugged in pi over 4 for x, I would get 1. And that's on the first, not that one. It's on the first one right here. So this right here, okay, because tangent is y all over x. If I take radical 2 all over radical 2 all over 2 divided by radical 2 all over 2, I do get 1, okay? And so we should already know that. It's already on our trig table of common angles and everything, okay? But now what if I ask this? What other values of x make it true? Think about that. Now, remember the periodic nature of tangents is pi. So if I go back to my unit circle, okay, well, look at this. All right, that equals 1 for tangent. Now, if I actually just go across 180 degrees because of pi, because pi equals 180 degrees and tangent's period is pi, look at that. What if I take negative radical 2 all over 2 divided by negative radical 2 all over 2, y all over x? Will that also equal it? Sure, absolutely. So 5 pi over 4 is definitely another value I could have here. So that means x could also equal 5 pi all over 4. But think about what I just did here. What I did was I added, watch now, what I added was 4 pi all over 4. Now I know 4 pi all over 4 is pi, right? Because I just divided by 4. So I'm just re-saying, pi is the same thing as 4 pi over 4, because if I just divide by the 4, I get pi, correct? So I can say, okay, plus 4 pi over 4, so I can add the periodic nature of pi, periodic nature of tangent, which is pi. And so 1 plus 4 gives me, 5 pi over 4. So if I do this again, watch. If I do this again, I get 9 pi all over 4. So this is an answer. This is an answer. This is an answer. Could I do it again? Absolutely. I could do it again. And so, wow, that's a weird looking pi. Okay. And then this is 13 pi all over 4. Could I do it again? Yes. Okay, 4 pi all over 4. And so this is going to be 17 pi over 4 and so forth. Now, here's the problem. When I ask you what makes this equation true, does it ever end? Like, can I continue going on forever and ever and ever without restriction? Yes, which is kind of bad news for us. You know why? Because who wants to literally write out all the values of tangent over and over and over and over and over and over and over for infinity, ad infinitum? No one's going to do that. Okay, which means we have to develop something that would help us, specifically this. Okay, this tangent. So tangent of x. Wow, what happened there? Tangent of x equals 1. I know that x will equal pi all over 4. And now if I plus pi and then multiply it by some integer n, that will cover all my solutions without me writing them out individually over and over and over again until I'm dead. And even then, I wouldn't have all the solutions because this can go on to infinity, right? And so this formula right here, just for tangent, and just because I know tangent's period is pi, this formula will actually help me. Why? Because now what I can do is I can say, okay, what if n is 1? If I say n is 1, all right, well, that means 1 times pi is that, and then I get 5 pi over 4 because pi all over 4 plus pi is 5 pi over 4. What if I said n equals 2? Well, then that would be 2 pi, right? And then 2 pi all over 4 is the same thing as 8 pi all over 4. So 8 pi all over 4 plus pi over 4 gives me 9 pi over 4, right? And then if I did n equals 3, that would be 3 pi over 4, which is the same thing as, I can't add. Man, look at me. I'm just dying. It's 3 pi, and then I need to times 12. There we go. Times 12. Right? And so 12 plus 1 is 13 pi over 4, and so on. Okay? And so, well, total brain dead there. Okay? So I can continue this over and over and over and over again if I just get n equals 4, n equals 5, and so forth. But this is the formula that I want to use. And that is what we're doing today. Okay, well, part of it. Okay, that's most of it. That's what we're kind of doing today. All right, but that is kind of how you do trigonometric equations. Again, I'm trying to find the value of x that makes that equation true. I'm going to show you on the graph. If I wanted to show you on the graph, tangent, let's just click on tangent here. Just regular tangent where my a is 1, my b is going to be, let's just say 1 as well because I'm looking at tangent. Tangent of x equals 1. And now what if I make my d negative 1? Okay, let's erase this. Ready? I get all that. What is that value? What is that value? What is that value? What is that value? Do those look like familiar values to you? We just found them, okay? And so what are we really trying to do? What we're really trying to do is find out where the trig functions cross the x-axis. Just like when I say solve the equation in algebra, what you're trying to do is solve where they cross the x-axis, right? That's what you're trying to solve for, yes? So that is what we're doing here. So if I literally type in tangent of x, okay, and then equals 1. Now what I'm going to get is this, okay? Now that's really awful, okay? But notice how my red lines are crossing exactly where they actually cross right there. Now to get not this funky stuff on the graph, all I have to do is just say minus 1, and then I get the exact same equation. Look at that. Okay, I get the exact same equation. So whether I have green or red, green, red, it doesn't matter, right? I get the exact same equation. Now, if I say equals 0, it gives me that again. So what am I going to do? I'm going to actually do this because I am interested in tangent of x equals 1. Okay, I equal it to 0, something that sounds familiar from algebra 2.2 from quadratics. It's the exact same thing. You equal the quadratic to be 0 on one side so you can solve it. And same thing here. You equal it to 0 on the graph so you can solve it. Okay? Now, we're not doing exactly similar to that, but I'm just letting you know you can use this as a graph. You can plug it in to Desmos as a graph, and you can actually see what values these are. These are the values that we got right here. Yes? And if I continued down, let me erase this. If I continue down and just scrolled over, okay, that's 13 pi over 4, 17 pi over 4. If I continued, I would get 21 pi over 4 and so forth. You see this? Yes? So I can continue this over and over again. But notice how my tangent graph is not restricted. What if I restricted it? What if I took just 0 to 2 pi and I restricted it like that? Okay? What would happen then? Well, what would happen is I only have two values that cross the x-axis. And those are the two values that you find on the unit circle. Why? Because the unit circle is 0 to 2 pi. 0 to 2 pi all the way through, from 0 all the way to 2 pi, 360. That is my restriction. So I have one value at 45 degrees right here. And then I have another value at 5 pi all over 4, 225 degrees. And those equal where tangent is 1. Those are my angles. Okay? If you plug it in your TI-36X Pro to even solidify this point even more, if I plug it in and do the inverse of tangent at 1, if I do the inverse of tangent at 1, because it's really an inverse function, I get 45 degrees. Now here's the problem. Okay, it only gives you 45 degrees. There's technically two solutions, especially if it's 0 to 2 pi. So yes, the calculator helps you, but there's only one solution? Okay, there's only one solution technically because the inverse functions only, if you remember, the inverse functions only came for tangent right here. It only looked on the right side of the unit circle. So remember that. And so obviously that's on the right side of the unit circle, not this. Okay. However, this is still a true equation, or this is still a true solution to my equation, technically. I just can't use it when I talk when I use inverse functions. So I'm just going on a huge rant and a huge rabbit trail. Okay, I just want you to connect. I want you to connect 5.7, the inverse functions, with the identities that we're about to show you. I also want to connect it to graphs and what we learned in algebra 2.2 and how we set it equal to 0 and where it crosses that axis, the x-axis. And I also want you to connect it to just our regular trig functions. If my periodic nature, if I keep adding pi, I get all these values. That's all I really want you to do. So without all of that, I'm going to stop ranting, okay? And what I'm going to start doing is teaching you the example. So the first part is this. You're going to isolate the trig part. The second part is you're going to solve the equation for the trig function. You're going to find out what value for the angle makes the equation true, and then you're going to add multiples of 2 pi, or for sine and cosine, or pi for tangent, of course, because the period of sine and cosine is 2 pi. The period for tangent is pi. Okay, so I'm given this equation. Let's get started on it. I really don't want to waste any more time. So how do I solve this? Well, first of all, you need to isolate the trig part. Clearly, this trig part is not isolated. Now, think of the trig part like a variable. Okay, just think of it extremely like a variable. It has to be like a variable, okay? So this sign right here and this sign, treat it like x. If you said this was x and that is x, and I said solve for x, you'd have no problem solving it. You'd have no issue solving that crap. But oftentimes when I see kids in trig, they see a trig function and then everyone loses their minds because they're like, oh my gosh, what do I do? You're solving it as it's an unknown. You don't know what it is. So if you really, really, really want to just plug it like this and then solve for x accordingly, and then at the very end put sine of x on that x, go for it. But I'm not going to do that. How am I going to solve this? Well, first of all, I'm actually going to subtract this all over. So that means when I subtract 5 times sine of x, what I get is negative 2 sine of x minus 2 equals negative 1. Notice how I'm solving this here. Now what I want to do is plus the 2 over plus 2. So then I have negative 2 times sine of x equals, that goes poofy, and then I have 1. And then I want to divide by negative 2 to both sides. That goes poofy, so I have sine of x equals negative 1/2. Now, of course, can I use my calculator to do this inverse? I could, because technically what this is x equals inverse sine. X equals inverse sine of negative 1/2, okay? But that's not going to give you your full solutions. Yes, you'll give you one of them, okay? And it's 30 degrees. It's pi over 3. But it's not going to give you all of them, okay? Or sorry, it's not 30 degrees at pi over 3. It's going to be like, it's in the third quadrant somewhere. Yeah, right here, third quadrant. So 7 pi over 6. So what, if you plugged it on the TI-36X Pro, even if you plug it right here, I'll even do it right here, guys. If I plug the inverse right here, so inverse sine of negative 1/2, what it's going to do is give you negative 30. Okay, what it's going to do is going to give you negative 30. Does that even help me? Sort of. Now remember, inverse functions, they say your sine is going to be on the right-hand side of the unit circle. And negative 30 is right here. So 11 pi over 6. So it kind of helps, sort of, but I can just use the unit circle and just say, okay, where does it give me negative 1/2? Where is y equal to negative 1/2? Because I know y is sine of x, okay, or sine of theta or whatever. So where's y equal negative 1/2? Well, right here. So what's my angle? There. Also, right here. What's my angle? There. That's all you need to do. You don't need to plug it into this, okay? That really doesn't help that much. It does help you because this is negative 30 degrees or pi over 6, okay, negative pi over 6. And so it does give you that, but doesn't give you the other angle, which means you need to use your unit circle or trig table of common angles. Okay, whatever you need to use. I don't care which one you use. You can use your trig table of common angles, or you can use this. I'm using the unit circle. I'm trying to find where y, my y coordinate, is negative 1/2, because that's where sine is negative 1/2. And I see two values here on the unit circle. So what am I going to do? I'm going to put them there. So what does x equal? X equals, it equals, first of all, 7 pi all over 6, because that's one of them. Right here, 7 pi all over 6, and then 11 pi all over 6. So I'm going to do x also equals 11 pi all over 6. Now, I found my values. That was step 3. So this was step 1, this was step 2, and then this was step 3. Now, step 4 is technically what I'm going to do right now. Step 4 is add multiples of 2 pi for sine and cosine. So what does that mean? That means I'm going to do plus, I'm going to do this in blue actually, I'm going to do plus 2 pi times n, okay? If you don't want to do that little dot n, then don't do it. But 2 pi n, and then plus 2 pi n. Why do I need to do this? Because read the title of this slide. It says general solution. Are you going to find out every single solution that fits with this equation ad infinitum, to infinity and beyond? No. Okay, you'll be dead before you do that. There's so many solutions to this because of the periodic nature of pi. It repeats every 2 pi integers. So I need to include something that will not stress me out by writing every single equation, because you'll never get there. I need to include something that will account for all the solutions. And that is what I did in blue, the plus 2 pi times n. The n will act as a sort of multiple here, okay? The n will act as a sort of multiple here, and then the 2 pi, of course, is my period of sine, okay? So this is for general solutions. Sometimes it will restrict it for you. So sometimes you'll see it like this. So from 0 to 2 pi. So solve the solutions from 0 to 2 pi. And that's what we're going to do next. But on Math Excel, and on your homework quiz and on the test, you will have some questions that will say, okay, give the general solution. In other words, if it doesn't give you an interval, it wants you to find the general solution. I'll say it again. If it doesn't give you an interval, like this one, do you see an interval anywhere on this problem? Yes or no? Nope. It just says solve. Okay, so since it says solve and it doesn't give you an interval, you have to solve the general solutions. You have to solve all solutions for this. Okay, but you can't do that. It's impossible, so you have to include the plus 2 pi n. If it was for tangent, like our last slide, I did plus pi n. Make sense? Okay, so that's for the general solutions. I hope I explained that clear enough. Let's erase and let's get into what if I'm given an actual specific interval. Now, am I going to do the plus pi n here? No. And why do I say plus pi n and not 2 pi n? Because it's tangent. So in this example, I'm not going to do the plus pi n, plus 2 pi n or whatever, because it's giving me an interval here. Okay, notice that's giving me an interval. All right, so I only want to find the solutions that make this equation 2 within this interval in terms of pi, in terms of radians. How do I do that? Well, here's the steps. So step 1, technically like a prerequisite step. You want to isolate the trig part. That's going to be always the first thing. Well, clearly this one's isolated, so I don't have to do anything. First step is find a new interval. I'm going to tell you what that means. And then the second step is you want to find what values that make that angle true, that make the equation true within the interval. You're going to build your quadrants and then add multiples of 2 pi or pi for tangent. Don't go past the interval, and then list solutions, solve, and simplify. So these are kind of weird. I'm gonna show you what it is. Now I will have to have a caveat here. Okay, preview this. First of all, when I solve this, it's going to be completely different than how Math Excel is going to solve it. I'm just going to let you know. Notice how this is what we call a multiple angle equation. So when Math Excel gives you a multiple angle equation, something that looks like this. So notice how this is not tangent of just x. It is tangent of 3x. Sometimes you'll be given tangent of 5x or cosine of 2x. Okay, that's what we call a multiple angle. In other words, your angle has something multiplied by it. That's what I mean. It has something multiplied by it. If it's 1/2, if it's 3, if it's 5, it's 10, that means it's what we call a multiple angle. And we need to solve it using these steps. Now, I solve it using these steps, and these steps are different than what Math Excel solves it for you. Math Excel solves it in a completely annoying way. It's so stupid, and I hate it. Okay, I taught it like the first couple of years I started teaching Trig when I was a new teacher, and the students were always confused. They always hated it. I hated it. I wasn't having any fun. And then I learned this new way a couple of years ago, and I was like, holy crap. This is amazing. This is so much easier, and you get the right answer all the time. And this is the steps I'm going to show you right now, okay? So I want to caveat that Math Excel, when you go through view an example, it will teach it to you differently, okay, than what I'm teaching it to you. So is the trig part isolated? Yes. Tangent 3x isolated. Find new interval. What is that? So this is my first step. Find new interval. What's my interval? Well, my interval is this. 0 to 2 pi, that's just my unit circle. What am I going to do? I'm actually going to multiply this. Watch what I do here. I'm going to multiply this by 3. Why? Because of this. Your x is multiplied by 3. So when I multiply this whole thing, this whole inequality by 3, what I get now is 3 times 0 is 0. 3 times x is 3x. Notice how it looks familiar. And then 3 times 2 pi is 6 pi. So this right here is my new interval. It's going to help me solve it a lot quicker and a lot faster. Okay? So now that I have my new interval, now I'm going to do step 2. So let's go to step 2. Step 2 is find values for the angle that make the equation true. So since the period of tangent is pi, so since my period is pi here, okay, and you may be thinking, well, it's not pi because that's b, right? So that's actually, 2 pi divided by 3. That's the period. No, hold on. If you're thinking that's my period, now listen very carefully. If you're saying, okay, well, actually, Mr. Carlson, it's 2 pi all over b. My b value is 3, so it's 2 pi all over 3. That's my period. So what the junk are you saying it's pi? Well, listen, kids. The reason why I have step 1 to be the new interval is because of that reason. Does that make sense? So I changed my interval, so now my period is no longer like this. This would be my period if, okay, if I was doing 0 to 2 pi. But I'm not. So technically, this is what I'm doing. My new period is from 0 to 6 pi. So now I would do 6 pi all over my b, which is 3. So now it's 2 pi, okay? Which, of course, correlates to this. But I don't want to confuse you about that. So those are only for like the really, really intuitive kids that catch that, okay? But I'm just going to let you know, tangent in general, my period is always going to be pi. Make sense? Forget everything I just said. Forget all of that. If that confused you, I don't want you to think about it, okay? I'm ordering you not to think about it. Okay, what I'm saying is, in general, my period for tangent is pi. Now, where on the unit circle does tangent equal 1? That's what I want you to ask. Where on the unit circle does tangent equal 1? Okay, tangent, so I'm literally going to write this out. Tangent equals 1 at pi all over 4. Okay, tangent equals 1 at pi all over 4. Now, if you may be wondering, well, it also equals 1 in a different area, like down here, right? Yes, but again, I'm going from 0 to pi as my period. I would have to repeat my period in order to get that value. So I don't care about that value. I only care about that value, okay? Because, again, my period is pi in general for tangent. Yes? So far, so good? Okay, so that means I'm going to start with pi. All right, so that means I'm going to start with pi. Now I'm going to go to my third step, and it's going to be build quadrants, okay? So I'm going to build my quadrant, and I'm going to start with pi all over 4. And I know pi over 4 is right there, okay? Now, I'm going to be adding multiple of 2 pi if it's sine or cosine, or add multiple of pi for tangent. So I'm going to be adding multiples of pi. Now, if I plus pi on this, what do I get? Okay, so if I plus pi right here, okay, plus pi, what is that? All right, so if I plus pi, that means this is, over 4 and this is 4. So that equals 5 pi all over 4, which is exactly right here. Okay, if I go back to my unit circle, this is exactly what I have here. Yes? 5 pi over 4? Great. So that means over here, I'm going to kind of go into the third quadrant and say, okay, 5 pi all over 4. Okay? Make sense? So I added 4 pi over 4, or pi, and then I got 5 pi over 4. So in other words, this is the first equation or first solution that I got. This is the second solution I got. So far, so good? Okay. I'm going to erase this. So now notice that we're going to now be adding just 4 pi all over 4 to each solution. So now, if I add 4 pi all over 4 to this, what do I get? Well, I get 9 pi all over 4. Okay? And this is what we call my third solution. Okay? But, sorry, when I add, I'm going to kind of go back and forth here. Sorry. So when I add 4 pi all over 4, I get right here 9 pi all over 4, because that's where 9 pi all over 4 actually exists. It's in the first quadrant. Okay, it's in the first quadrant. Now, if I add another 4 pi all over 4 to this, what I get is 13 pi all over 4. If I add another 4 pi all over 4, I get 17 pi all over 4. Now, notice I'm still not past 6 pi. So because 4 does not go into 17 6 times, right? So I'm still solid. I'm not going past my interval. I'm good. Okay? Let's continue. 17 pi over 4 plus a 4 pi all over 4, which is pi, is going to be 21 pi all over 4. Okay? So far, so good? Okay. If I add 21 pi over 4 to 4 pi over 4, I get 25 pi all over 4. Now, here's what we notice. Can 4 go into 25 6 times? Yes. And then a little bit more, which means now this value is past my interval. I cannot use that value because it's past 6 pi. Okay, my new interval, right? Okay, so now I have 1, 2, this is my third solution, fourth solution, fifth solution, and sixth solution. So I have 6 solutions that make this equation true in my new interval. But here's the problem. So before I get to that, let's actually list my solutions. So this is going to be for my fourth step. My solutions are going to be 3x equals, catch what I'm doing here, watch. So this is pi all over 4, 9 pi all over 4. It doesn't matter if you do 1, 2, 3, 4. It doesn't matter. I'm just going to list them out. And this is going to be 17 pi over 4. And then this is 5 pi all over 4. This is going to be 13 pi over 4. And then 21 pi over 4. So I have 6 solutions. Okay? And I put 6 because I was thinking about 6. Okay, so over 4. Awesome. So now watch carefully what I do here. These are my solutions. Watch. These are my solutions given my interval that I created, my 0 to 6 pi interval. These are my solutions. I don't want solutions from 0 to 6 pi. I want solutions from 0 to 2 pi. So how do I do this? Well, now look at my x. I said 3x equals because that's what it is, 3x equals. Now watch. What if I multiply by 1/3 to this? That goes poofy, that goes poofy. And now I get to step 5 and I get x equals, which is what I want. What does x equal? Now watch, watch, watch. So now when I do to one side, I must do to the other. So technically, all of these, I'm multiplying 1/3 to it. I'm multiplying 1/3 over and over and over again to every single value. Okay, I'm multiplying 1/3 every single value here. Okay, very annoying, but I'm telling you, it's way faster than how the book describes it, how your Math Excel describes it. So now let's do this. What is 1/4 times 1/3? Well, that is pi all over 12. Okay, that's pi over 12. What is 9 pi all over 4 times 1/3? Well, the 9 and the 3, they go poofy. Okay, so then the 9 divided by 3 is 3, so I get 3 pi all over 4. All right, right here. So that one's done, that one's done. Now let's go here, 17 pi over 4. Well, 17 pi over 4 times 1/3 is 17 pi all over 12. What about 5 pi over 4? Well, same thing. 5 pi over 4 times 1/3 is going to be 5 pi all over 12. Okay, 13 pi over 4 times 1/3 is going to be 13 pi all over 12. And then 21 pi all over 4 times 1/3. Well, that goes poofy because that becomes 7 because 21 divided by 3 is 7. So 7 pi all over 4. So that's my last answer, 7 pi all over 4. These are my solutions. Now, you may be thinking, oh my gosh, you for real? That blows. You should watch me do what Math Excel wants you to do, okay? That blows way more, so trust me. Okay, I'm going to do another example like this, but before I do that, I want to show you how to do this on Desmos because you absolutely can do it on Desmos. So if you're thinking, oh my gosh, that sucks so much, I don't have any time to do that, do not worry, do not fear. Desmos is here, okay? So I will show you how to get all of these on Desmos because it's amazing and Desmos is a great tool, okay? So let's do that. So I'm going to erase this. Now, my actual equation was this. Tangent of 3x, okay, equals 1. Now, of course, I don't want equals 1 because that looks crazy. Like, why do I want that? Let's subtract that 1 over and do minus 1. Now, watch, watch, watch. I wanted a restriction, though. Restriction between 0 and x and then 2 pi. Okay, that was my actual original restriction. This is what the problem gave me. Now watch what it gives me. Ready? Pretty great, right? Come on. You know. Okay, pretty awesome. Where it crosses the x-axis is where all my solutions lie. I'm done. Okay, now how do you solve that using this graph? Okay, I'm going to show you. So I'm going to go up to tangent. I'm going to select it. Now notice how it's sort of the same thing, but watch, watch, watch. Tangent, now follow my variables here, okay? I did this because some of you may not want to actually switch your variables here, and if you don't want to do that, you can just type it in like this into a blank random Desmos graph, and you'll get the right answer. I'm not going to do that for the rest of this time. I'm actually going to do it this way. My b value of tangent is 3, so I'm going to change that to 3, okay? Notice what happened here. And then my d value was -1, okay, because I switched it over and equaled my equation to 0 and said -1. So that's my d value. That's the thing that moves it up or down. So I said I want to make it -1. There is no c value attached. If there was a c value attached, it would be in parentheses. But technically my c value is 0. That's my c value, so I'm going to make it 0. And then my a value, of course, is 1 right here. And we can say 1. It doesn't do anything. Okay, notice what I'm doing here? So I can adjust that to be this. Now watch. Even if I made this like red here, it doesn't matter because it's the exact same equation. Okay? And either way, I get my solutions, my 6 solutions. Pretty freaking awesome, right? Now, the cool thing is I'm not going to actually use Desmos. Okay, I'm not going to solve it completely by hand. I'm going to solve all of them completely by hand because I think it's important for you to actually solve them all completely by hand. And sometimes Desmos does not work, especially if you're given like I can't really, if it's like a really weird odd function or really not function but angle, it may not actually show up here. Okay, if it's a really intense angle, it may not show up. But just in case, if you're like, I don't have this, remember you can always go to your settings here and you can always change your x-axis to be a step of pi over 2. That's how I can find those because I make sure that there are pi over 2 there. Okay, so make sure you change that and so you can get these values. Okay, awesome. That's how you do it on Desmos, and we do get the exact same answer. I don't want to take any more time from that, so I'm going to erase this and we're going to get started on the next example. Okay, same steps as before. It is isolated, so that's a check mark. Find the new interval. So I'm going to change this and change it to my new interval. So what's my first step? My first step is this. I see that this is technically this is sine of 1/2 times x, right? So that means I need to multiply by 1/2, multiply 1/2 to all of these, this solution here, okay? So that means I get 0, and then I get x all over 2, which is exactly my half angle, my multiple angle here. That's a multiple angle. 1/2 is still a multiple angle. And then this is, whoops, I don't want to do that. And then this is pi, okay? So this is my new interval, 0 to pi. Now, my second step is going to be find, my period is 2 pi, okay? My period is 2 pi for sine. So since it's 2 pi for sine, that means I'm going to find on the unit circle where sine equals radical 3 all over 2. So sine equals radical 3 all over 2 on these intervals, on these angles. So radical 3 all over 2, so equals at pi over 3. And then I can literally just cross right here. Look at that. Isn't that cool? Okay, whoops, sorry, because I don't want to do that. Forget what I just said. because it's 2 pi, right? I don't want to do pi. It's right across here. So right here, radical 3 all over 2. So these are my two angles, okay? These are my two angles that I have, and then it repeats 2 pi over and over and over again on these two angles. So the first example that I did only had one angle from 0 to pi, but my whole unit circle, when I take my whole unit circle here, okay, I have two angles now where it fits my initial solutions. It fits my initial equation, okay? So now I have pi all over 3, and then I have 2 pi all over 3. Okay, now what I want to do is I want to build my quadrants. And I'm really going to just add 2 pi or 6 pi all over 3 because 2 pi equals 6 pi all over 3. And I want to add this specifically to those values and see if I go over pi. And you'll probably find out that we will. Okay, but right here I have 2 pi. Sorry, not 2 pi over 3. I have pi over 3. Right here I have pi over 3. And then right here in the second quadrant, I found that to be 2 pi all over 3. Now, if I add 6 pi all over 3, so 6 pi all over 3, I know this is a solution already. I know this is a solution already from Desmos, from my unit circle. If I add this, this actually equals 7 pi all over 3. But here's the problem. Is it past my interval of pi? Does 3 go into 7 at least one time? Yes. So I actually cannot use that. Okay, so I can't use that. Now, if I add 6 pi all over 3 here, 6 plus 2 is 8. Okay, this equals 8 pi all over 3. Does 3 go into 8 at least or more than one time? Okay, it goes into at least once, but does it go into it more than one time? Yes, which means it's past my new interval of pi, which means I can't use that. Which means for 4, what are my actual solutions? My actual solutions are this. So 1/2 x equals, because that's my half angle, that's my multiple angle, equals 2 pi all over 3, comma, pi all over 3. Okay? Those are my two angles that I found on the unit circle, but also found that only exist within my new interval. So I'm going to list them out. And then step 4/5, step 5 is to, of course, simplify and solve. So I'm going to times by 2, and I'm going to take all of this and times by 2. So now 2 pi times 2 pi all over 3 times 2 is 4 pi all over 3. Okay, that's my first solution. And then 2 pi all over 3 is my other solution, because 2 times pi over 3 is my next solution. What does this mean? This means these are my answers in my original interval, which is exactly what it asked for. So if you're maybe wondering, like, why do we need to find this new interval? We find the new interval to help us solve, Okay, that's really what it's asking us to find. It's very difficult to find the half angle, okay, of what this equals in the original 0 to 2 pi. But when I'm given the half angle here, and I just want to find, okay, what values of sine equals radical 3 over 2 within this new interval, it's way easier to solve it that way, because then all I have to do is look on the unit circle, which is exactly what we did. And then we double check to see if there's any extras. Like in the last example, there was a lot of extras. In this example, there's no extras. They both go past my new interval. And then after that, I list them out. I want to solve for x and not my half angle. So I need to kind of go back to my original interval. And then I multiply by 2 on both sides, and I get x equals my actual original interval. X equals these solutions. So it's kind of like a trick. It's kind of like a trick, a short way to find our solutions for these equations, okay? I hope that helps. And that's how you do multiple angles and how you solve trigonometric equations over an interval. Again, this is not a general solution. I don't need a plus 2 pi n here because it wants in a specific interval. If this interval did not exist and it said solve, then yes, I would be plussing 2 pi n right here on my intervals, or on my solutions. I would be plussing 2 pi n on my solutions here. to account for all the solutions that I can't necessarily add because it's infinity. Okay? Does that make sense? I hope it does. I'm going to erase. Those are probably the hardest examples, honestly, that I have for you. And if you're like, really? Yes, those are probably the hardest examples I have for you. The rest, I'm going to be doing quadratics and factoring. And so, again, this is a two-part, so I only have a couple more examples for you. But really, the next couple of examples, and what I'll kind of do next, the next lesson tomorrow, is when solving for trig equations involving quadratics, you're going to use a variety of methods. You're going to solve it using a quadratic. You're going to solve using factoring, GCF. But you're also going to solve using identities, but that's going to be tomorrow. We're going to hold off on that. Really, what the goal is when solving these is getting sine of x equals a number. That's really the goal. The goal is to get sine of x equals some number. If you can get that, then you can look at your unit circle and then you can start solving them. Okay? Of course, you can use Desmos. Okay, if you get the right interval, and I may show you on this next one exactly how to use Desmos on it, but yeah, okay. Let's go to town. So I'm given this. Okay. Now, I need to solve the trigonometric equation in quadratic form. Now, let me ask you a question. If you were given this, 2x squared plus, see what I was about to do? I was about to do cosine there. Plus x minus 1 equals 0. And if I said solve, could you solve for it? This is what we call a divide and slide problem. What if you had algebra 2.1 with me, or 2.1 with me, you should remember a divide and slide problem. Okay, but I'm going to solve that with you. So what does this mean? I'm not going to solve it that way with just the x's, but that's exactly what it is. I need you guys to get into the I don't know, just the habit. There you go. The habit. Get in the habit of looking at this cosine and trig functions as just a regular equation. It is literally just a regular equation. It doesn't matter. You understand? It doesn't matter. So I can literally look at this and factor it like normal. Now, how am I going to factor it? We use what we call the divide and slide. How do I solve it using the divide and slide? Now, remember, I look at my first coefficient of the leading term and then this one, and then I multiply them. So 2 times negative 1. This equals negative 2. Now, what factors of negative 2 somehow, some way add up? This is my first step. Somehow, some way add up to this, positive 1. Well, I have a 2 and then a negative 1, right? They add up to 1, or subtract to be 1. So now my second step would be to build my basic template, and that would be cosine of x plus 2. If this was x, it would be the exact same thing. I'm just doing cosine of x. So cosine of x and then minus 1. It's just like factoring a quadratic, but in trigonometric form. And then equals 0. Okay? I'll tell you why this is important. This interval is important here. Okay, now what I do for my third step is I divide. So divide by my leading coefficient. So divide by my leading coefficient 2. Divide by this. Okay? So the rule says if it doesn't divide, you slide it. Okay? And so this divides unevenly. So now what I have is cosine of x plus 1. This does not divide unevenly. So originally, if you remember, what we would take is that 2 and we would slide it in front. So this would be 2 cosine of x and then minus 1 equals 0. Okay. Now, if you remember, my fourth step would be to actually solve for this. Now, this is my zero product property, which means each product gets equal to 0. So that means I have, number 1, I have cosine of x plus 1 equals 0. And then my next one, I have 2 cosine of x minus 1 equals 0. Okay? And then I solve each one for cosine. So this is cosine equals negative 1. And then this one right here is going to be cosine equals 1 all over 2 when I add the 1 over and divide. Now, I'm going to pause right here. Now, you could have right here, you could have just said this instead. Instead of sliding it over, you could have done cosine of x minus 1/2, and then you could have just done that and added the 1/2 over. I will do that from now on. I just wanted to remind you that that's the divide and slide. Now, you're maybe wondering, well, why do I need to slide it over then? The divide and slide was a method that I formulated to help you when solving and factoring expressions, not equations. But I use the name divide and slide because it helps ring a bell like, oh, okay, this is the method that I'm going to use. But technically, no, because it's an equation, we don't need to slide that over. We can actually keep that negative 1/2 and then just add it over as such, like what I did down here. Either way, you get the right answer. So if you want to slide it over and then solve for cosine after, that's fine. It's still the exact same thing, okay? Or you can just say, okay, I know I don't need to slide it over because it's equal to 0, and I'm just going to solve for cosine anyways. And so I'm just going to add the 1/2 over to the other side, and that's what cosine equals. If you want to do it that way, perfect. But these are my two solutions, sort of. Really what I want to find is x equals. But like I said in the last slide, this is really what you want to do. This is like the actual this is what, like, the goal, what you want to do. You want to get it into this format. And I did get it into this format, which is amazing. So now all I need to do is say, okay, where on the unit circle, 0 to 2 pi, because this is really the unit circle. Okay, 0 to 2 pi is the unit circle. Where on the unit circle does cosine equal negative 1? Where on the unit circle does cosine equal 1/2? So let's go there. So on the unit circle, where does cosine equal negative 1? Remember, cosine is my x, right? Cosine is my x. So right here is where it equals negative 1 on my x. So that is pi. So I'm going to go back. I'm going to say pi. Okay? Now, where does it equal 1/2? Because this is one of my solutions. Where does it equal 1/2? Let's go. Okay, 1/2. I'm looking. Okay, right here, 1/2. Okay, pi over 3. All right, that's one of them. And then I'm looking, and right here, 5 pi all over 3, right here, 1/2. Okay, so I have 3 solutions. So that means I'm going to write in pi over 3 and 5 pi over 3. So I'm going to go back. So pi all over 3, and then 5 pi all over 3. I'm done. Happy face. Those are my answers. Done. Okay? How are we feeling? We feeling good? Now remember, I could solve this just like a quadratic. If I solve this just like a quadratic, I would still get x equals, okay, negative 1 and then 1/2. I would get that. But the problem with that is really what you're saying is cosine of x equals negative 1 and 1/2. And you're not technically done yet. Like, you have one extra step left to do, and that's my 5th step, is to actually do the inverse. By the inverse, I mean look on the graph, look on your unit circle, because that's my interval, of where cosine actually does my x value, because cosine of x does equal my x value, where cosine, my x value, equals 1/2 and negative 1, boom, boom, and boom. Okay, just like this. Where does it equal negative 1? Pi. Where does it equal 1/2? Pi over 3 and 5 pi over 3. Notice how I'm asking for angle measures. Okay, these are angle measures, so radians. So 180 and then 60 degrees, and pi over 3 is 300. Okay, all right. And it's not asking for evaluations. It's giving us evaluations. Okay, the evaluations, the side lengths, the ratios. I want to do the inverse property of that. Now you can plug that in your calculator, cosine of pi. If you actually did that, cosine of pi, like inverse of negative 1, you would get 180, which of course is pi. So I can actually change this right here to radians, and I would get 3.14, and that would be, of course, pi, right? I could do that if I wanted to. But it seems like a little bit extra work when you could just look on your unit circle or your trig table of common elements, and it would solve it for you. Now, I'm going to show you how to actually plug it into Desmos. So I'm going to erase this. I'm going to take this away. I'm actually going to just show you how to plug it into Desmos. I was given 2 cosine squared x plus, and then cosine x, and then minus 1. Now this is what the graph looks like, and now I was restricting it from 0 to 2 pi. So I need to make sure I do that, my restriction, and then those are going to be my answers. Pi over 3, pi, and then 5 pi all over 3. Those are my exact answers here. Pi over 3, and 5 pi all over 3. Pretty cool, right? Again, I don't like really showing you how to show it on Desmos because I feel like it's taking up all the math. Like, this is great math, and I love this. But yes, you can double check yourself on Desmos, and it's a blast, okay? It's really rather amazing. All right, so let's move on and do our last couple examples here. Okay, I am given this. So what do I want to do? Well, I notice that it's still my unit circle. So let's solve this. I want to isolate this now. I can't factor it really, but what I'm going to do is solve it differently. So notice how this is in the form of 4x squared minus 1 equals 0. How would you solve your quadratic equation like that? Okay, maybe you're thinking plugging into Desmos. Okay, fair enough, but I'm not going to do that. Add the 1 over. So 4 sine of squared x. I'm just solving for sine here. And then add the 1 over is 1. Divide by 4. That goes poofy. So I'm left with sine squared x equals 1 all over 4. Now watch this. I'm going to, because this is squared and I can do it, square root. The square and the square root go poofy. So now what I'm left with is sine of x, which is what I want. And then what I'm left with is not just plus, but plus or minus. I'm left with plus or minus 1/2. Okay, that's the square root of 1/4. It's plus or minus 1/2. Now, this, of course, helps me get to my answer, but it's not my answer. So now what I need to do on this step is use the unit circle or the trig table of common elements. Where on my unit circle, okay, where on my unit circle does the y-coordinate, sine, because sine is y, where the y-coordinate gives me negative 1/2 and positive 1/2. Where on the unit circle does sine give me, my y-coordinate, positive 1/2 and negative 1/2? Boom, right there, okay? But also, right here, negative 1/2, and then right here. So it's actually 4. So that means 5 pi over 6, 7 pi over 6, pi over 6, and 11 pi over 6. So I'm going to go over here and write them all down. So pi over 6, 5 pi over 6, 7 pi over 6, and then 11 pi all over 6. That is where on the unit circle, where I find positive 1/2 and negative 1/2. Okay, for my y-coordinate, because remember, sine is y. Sounds good? Okay, and so I just record those and boom, do it right here. Now, what happens if it did not give me an interval? What I would have to do, guys, is do pi all over 6 plus 2 pi n. And then I would do, comma, 5 pi all over 6 plus 2 pi n, comma, and then I would do 7 pi all over 6 plus 2 pi n, and then 11 pi all over 6 plus, plus 2 pi n. My mistake. Plus 2 pi n. So if it didn't give me an interval right here, this is what we call the general solution. Okay? The general solutions. But because it gave me an interval, specifically find me the solutions between 0 to 2 pi, which is the unit circle, that these are my solutions. Does that sort of make sense? There's a difference between not giving you an interval and giving you an interval. If it gives you an interval, then you only find the things that are within that interval. And of course, this is between 0 and 2 pi. Now notice it's not a multiple angle either. So there's no like 3x in here. So I don't need to find a multiple angle, right? Yes? I don't need to actually change my interval here. Because this is only just sine of x, sine squared x, and this coefficient right here, my b value of my trig function right here is just 1. I want to keep it between 0 and 2 pi. I only need to change that interval when that b value, that number before the x, is tampered with. Okay? But since it's not, I keep 0 to 2 pi, I use the unit circle, I solve, and then those are my answers. And if I want it in general form, boom, there it is. I'm really trying to explain it like well. I hope I am. I hope I'm really explaining it well. Okay, because that's why the videos are so long, because I'm trying to explain it so well. So now this is our last one here. What if I want to factor? Well, I can factor this, but I want to set it equal to 0 first. So I'm actually going to subtract 3 tangent x, and then this is going to be plus tangent x, and then sine squared x, and then equals 0. Notice how I'm still going to be using my unit circle. So now what I want to do is I'm going to take out a tangent. Okay, let's take out a tangent and see what we get. So I'm going to take out a tangent, and then I get -3, and then plus sine squared x. -3 plus sine squared x. So now, since this is the zero product property, I have my first equation, which is tangent of x equals 0. And my second equation, which is -3 plus sine squared x equals 0. Okay? So now, what's tangent of 0? Well, tangent of x equals 0. I use my unit circle or my trig table of common elements, and then, or common elements. What is this? Freaking like chemistry? Please. Okay? I use my trig table of common angles, and I want to find where tangent is 0. So tangent of 0 is probably harder to find on the unit circle, but you can still find it. Remember, tangent is y all over x. So my y right here, 0 all over -1 would be 0. So that means pi is my first solution. And then my second solution is actually just literally opposite of it. 0 all over 1, so 0 all over 1 is still 0. So that means 0, my radian measure 0, my degree measure 0, is also a solution. So these are 2 of my solutions so far. And now when I go over here, I can add the 3 over. So I have this, so plus 3. And now I want to square roots. And so sine of x equals radical 3 or plus or minus radical 3. Now watch. Is there anything on the trig table of common angles or the unit circle where it will give me positive or negative radical 3? Now for tangent, yes, but for sine is my y-coordinate. I can easily look on my y-coordinates and see if there's any radical 3 here. And no, I don't have any radical 3. I have radical 3 all over 2 or negative radical 3 all over 2, but no just simple radical 3. So since I have no simple radical 3 here, what we say is this is actually a no solution. So this right here is a no solution. So my only 2 solutions for my whole equation I'm given are these answers, pi and 0. Okay? Awesome. Awesome, awesome. Of course, you could have plugged that into Desmos if you wanted to. I'm not going to show you, but you can definitely plug it into Desmos if you would like, and you would still get those answers. All right? So let's erase this, and let's finish up. So what did we learn? We learned how to find all solutions of a trigonometric equation. So that's basically the general solution. That's what we found, the general solution. We solved equations using multiple angles, kind of using the back and forth between the quadrants, okay, and getting a whole new interval and adjusting it accordingly. And then we solved trigonometric equations using quadratic form and using factoring to separate different functions in trigonometric equations. Okay, so remember, retakes for your Unit 1 tests are still due this Friday by 4 p.m. Be sure to go onto Math Excel and do your homework, guys. But If you have any questions, just email me and I will try to get back to you as soon as possible. I've been very busy this week, but I'll try to get back to you as soon as possible. But thanks for hanging in there. This is Mr. Carlson, C Squared Mathematics. Peace.